In the previous lecture, we started the discussion on the topic of decoders, which are essentially the opposite of multiplexers. We saw how we can essentially make use of the multiple outputs of the decoder to realize one or more logic functions. So as we had established, a decoder has some n number of select inputs and 2 raised to n number of data outputs. Now, just like a mux, a decoder also has an enable input. So again, the enable input is to activate the logic functioning of the decoder. So enable, just like the case of mux, can be of two types: active high or active low. And in the previous lecture, we saw from the discussion that the outputs of the decoder can be either active high or active low. So therefore, if you combine the enable functionality into the decoder, you can have active high output decoder with active high enable. You can have active low output decoder with active high enable. You can also have active high output with active low enable and active low output with active low enable. All four combinations are possible. So therefore, let us see one or two such examples. One example that we can see is active high output decoder with active high enable. So an active high enable means what? So if the EN input is 1, then the decoder is working. And active low means if the enable input is 0, then the decoder works. Otherwise, it is inactivated, just like a mux. So therefore, again, let us take the example of a 2:4 decoder. That is one of the simplest to understand. So you have two select inputs A and B, and along with that, you have an enable input. And four outputs Y0, Y1, Y2, and Y3. Now, if the enable input is 0, what is being said? The enable is active high. So if the enable input is 0, that means the decoder has to be deactivated. Therefore, it does not matter in this case what is the value of A and B. All the outputs are inactive. Now, we know that this decoder in question, this decoder in this discussion, is an active high output decoder. So therefore, none of the outputs would be active. So therefore, all of them would be 0. Now, if the enable is made 1, then we can have 4 different combinations of the input, where the decoder is expected to work just like the way we know it works. So in case of 0, 0, the output Y0 would be 1, and all of the remaining ones would be 0. Now if AB is 0, 1, Y1 would be 1, and the rest of the outputs would be 0. Now if A and B are 1, 0, Y2 would be 1, and the rest of them would be 0. Likewise, Y3 would be 1 when A and B are 1 and 1. So therefore, if you want to show the logic diagram, it would look something like this. The enable input would be shown here. If you want to make it enable, you have to give 1 over here. And there would be 4 outputs: Y0, Y1, Y2, and Y3. Okay. This is a 2:4 decoder. Let us take one more example. For a clearer understanding, let us take an active low output decoder with active low enable. So this is just the converse of what we discussed. So again, let us take a 2:4 decoder. 2 select inputs A and B, 4 outputs Y0, Y1, Y2 and Y3 and an enable input. Now, if we want to activate the decoder, the enable is active low. So therefore, this must be given 0. Now, if A and B are 0, 0, then Y0 is activated. That means it will be 0 because it is an active low output. And the rest will be 1. Now, if enable is 0, A and B are 0, 1, then Y1 will be 0 and the others will be 1. This is the way. This is the normal function of the decoder. But if enable is made 1, then the decoder is deactivated. And it does not matter what A and B are, all the outputs are deactivated. Now deactivated means what? It is active low, so all of them are high. This is the meaning of active low enable and active low outputs. So likewise, I leave it to you as an exercise to find out how you can decipher the working of decoders with active high output but active low enable, or the converse, active low output but with active high enable. It is not a very difficult job. Now, having established this, let us continue our discussion on the decoder and how you can use the decoder to achieve certain logic functions. Now, suppose we have a logic function which looks like this. So it's a 2-variable function and there are 2 minterms, 1 and 3. Now let us say we have a 3:8 decoder, sorry, a 2:4 decoder with active low outputs and an active low enable. So if the enable is active low, it is again shown with a bubble and you have to connect it to ground to show that it has to be activated. Now active low outputs means there are 4 bubbles and 2 select inputs A and B. In this case, the outputs of interest are Y1 and Y3 because they will go to 0. They will go to 0 if the values of A and B are either 0, 1 or 1, 1. But just as a continuation of the discussion from the previous lecture, let us see how we can implement this function. So finally, we need to obtain the output Y. So if A and B is 0 and 1, Y1 will become 0. And if A and B are 1, 1, Y3 will become 0 while the rest will be 1. So for these two input combinations 0, 1 and 1, 1, we want that the output should be 1. So therefore, the moment either of these two lines become 0, the output must be 1. So therefore, we need a gate where if any single of the inputs becomes 0, the output will be 1, and that is nothing but a NAND gate. This is why. This is why. You can also realize the same function by using y0 or y2. It's not very difficult. So essentially, the max terms you will have to now look at. Now the max terms are what? 0 and 2. So when either of this becomes 0, you want the output to become 0. When either of this is 0, you want the output to become 0. That is when AB is either 0, 0 or 1, 0. So therefore, you can simply use a you can use a AND gate to get this task accomplished. So it's not very difficult to do this. Now, let us go one step further. Let us look at a 3:8 decoder. So a 3:8 decoder has 3 select inputs and 8 outputs. The outputs are y0, y1 all the way till y7. Now, let us assume that it has an active low output and active low enable. And let us say I want to realize the functioning of a full adder using this decoder. So the full adder looks like this. The truth table, there are 3 inputs and 2 outputs, sum and cout. So in this case, the sum would be 0, 1, 1, 0, 1, 0, 0, 1, and the carry would be 0, 0, 0, 1, 0, 1, 1, 1. So then, let's suppose we want to write the sum and cout in the condensed sub form. The minterms are 1, 2, 4 and 7 for sum. And for carry out, the minterms are 3, 5, 6 and 7. Now how do we realize this using a 3:8 decoder? So let's draw it first, the decoder, what it will look like. The symbol is an inverse trapezium. The select inputs are A, B and Ca. There are 8 active low outputs. And there is an enable which is active low. So therefore, first thing we will connect it to 0 or ground. So y0, y1, y2, y3, y4, y5, y6, y7. Now let us say we will hunt for the minterms. So for sum, we saw the minterms are 1, 2, 4 and 7. So 1, 2, 4 and 7. So when any of these inputs, when any of these lines, output lines, become 0, that is when they're activated, then the sum should become 1. So once again, that means we need a gate where if any of the inputs become 0, the output will be 1. So we will need a NAND gate. So all of these we will send as inputs to the NAND gate. And for carry, the minterms are 3, 5, 6 and 7. So 3, 5, 6 and 7. So once again, when any one of these 4 lines becomes 0, the carry output should be 1. So therefore again we will need a NAND gate. This is Cout. Now suppose I had to do the same task using a 3:8 decoder but active high outputs. Then the task would be even more simple. So in this case, I am not showing the enable logic because it's not very important at this point of time. So once again for sum, the minterms are 1, 2, 4 and 7. Oops, I drew this as active low, but it should be active high. So therefore, let me just cancel this and draw a fresh one. Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7. So then over here, like I was saying, for sum, the minterms are 1, 2, 4 and 7. So now here, when any of these 4 lines get activated, that means it's a 1. Then my output should be a 1. So we need a gate where if a single of the inputs becomes 1, the output also becomes 1. So therefore we will need an OR gate. So the inputs will be 1, 2, 4 and 7. Then comes carry, where the minterms are 3, 5, 6 and 7. Again we will need an OR gate to combine them, because when any of these inputs becomes 1, the minterm is activated and the output would also become 1. That's it. Again you can show an enable. Suppose it's active low, then you can connect it to ground. As simple as that. Likewise, you can do the same for both active low outputs and active high outputs by hunting for the max terms. That you can do. So the process for that would be just the converse of what we are looking for, because if you're looking for max terms, then finally you want the output to be 0. Therefore, you want the outputs to be 0. Let's see how to do that. Let's do the same exercise. Looking for max terms. But 3:8 decoder with active high outputs. So for some, the max terms are 0, 3, 5 and 6. And for carry out, the max terms are 0, 1, 2 and 4. Now we have this decoder with active high outputs Y0, Y1, Y2, Y3, 4, 5, Y6 and Y7. Inputs are obviously the same. Select inputs A, B and C in. Now comes the fun. We are looking for the max terms. So let us say for some 0, 3, 5 and 6. Zero, 3, 5 and 6. So whenever any of these lines become activated, that is when they become 1, the output should go to 0. Because we are ultimately interested in the max terms. So therefore, the question now is, which gate gives a 0 when any of its inputs become 1? The answer is a NOR gate. So this is the logic for sum. And for carry out, we need 0, 1, 2 and 4. Once again, the logic would not change. We would still need a NOR gate, because if any of these active high outputs becomes 1, my NOR gate would give me a 0, which will correspond to the max term. And at all other times, we will get 1. This is C out. This is C out. Similarly, you can look for max terms also using 3:8 decoder with active low outputs. In that case, all you need to do is to use an AND gate. As simple as that. So therefore, we are using NAND or NOR and AND, depending on what kind of decoder it is. You can, don't forget to show the enable. Let us say if enable is active high, then you can give it 1. That is how do you do this. So it's not necessary that you need to use all the available outputs from the decoder. There will be certain cases when not all of the outputs will be used. We have come across some of those conditions, although we did not explicitly mention that. So now let us ask ourselves, How can we realize a large logic function using a smaller decoder? How can we realize a large logic function using smaller decoders? So let's say for example that we need to realize a 3:8 decoder. We don't have one. We need to realize a 3:8 decoder in spite of the fact that we don't have one, but all that we have are 2:4 decoders. We have 2:4 decoders. Now here is the place where you will see the decoder would seem to have less advantage as compared to a multiplexer. You can realize logic functions of more number of variables using multiplexers with select inputs of less number of variables. But using only one small multiplexer, you can do that. But for decoders, it's very, very difficult. If you have 4 variable logic functions, you will need a 4:16 decoder. Or if you have 3:8 decoders, you will need 2 of them. In our present problem, we are trying to realize a 3:8 decoder. That is, we have 3 select inputs. But we are having only 2:4 decoders. So therefore, we will need 2 of these. So therefore, let us say that these have active high outputs. Active high outputs. So let us say y0, y1, y2 and y3. These are there. This will also have y0, y1, y2 and y3. These will have 2 select inputs, each of these. And let us say there is a active low enable. Let's say we want to implement the same full adder A, B, C in, or rather let me just draw it over here. This is the truth table. Now we have 2 decoders, 4 outputs over here, 4 outputs over here. So therefore what we can do, we can partition the truth table horizontally this way into groups of 4 and 4. Now what we are noticing is that B and C in are kind of repeating. 00 to 11 in the first half, 00 to 11 in the second half. So therefore, let us use these 2 as the select inputs. So when B and C in go from 00 to 11, any one of these will be activated. But let us say when B in is 00, y0 will also be a 1. Here y0 will also be a 1. We don't want that. We want that there should be some distinction between these two y0s. So who will give that distinction? If B and C are both 0, 0, this y0 will be 1, even this y0 will be 1. But we don't want that. We want that there should be a unique identifier, and that is helped by the variable a, which we have not considered. So what we can do is, for the upper decoder, we can use a as an enable input. Because here a is 0, so therefore this will be enabled. Here what we can do, we can use a bar as an enable. Because here a is 1, so therefore whenever a is 1, the lower half of the truth table would be activated. Is that fine? We are essentially using a to partition the truth table and to activate either of these decoders. Let's see how. So let us say a is 1, 0, 1. So when a is 1, 0, 1, what will happen? A is 1 means the upper decoder will be inactive and all of these outputs would be 0. Now when a is 1, 0, 1, as we were discussing, a bar will be 0. So the lower decoder will be enabled. And 0, 1 means B and C in Y1 will be active. Y1 will be 1, rest all of these will be 0. So you can work it out for yourself and see that using this arrangement, all of these outputs will have 1, 1 and rest of the 7 outputs would be zeros. So the question is, how do we realize this? These are active high outputs. How do we realize the sum and cout functions? So for the sum function, the minterms are 1, 2, 4 and 7. We can actually number these in the minterms. So therefore, when any one of these becomes 1, the output will be 1. So let's show how we can do this. We will need an OR gate, as we have discussed earlier. And the carry will be also an OR combination of 3, 5, 6 and 7. This is carry out. This is the way we can implement a 3:8 decoder using two 2:4 decoders. So that's how it is. Now let us say, suppose we make both decoders enabled at the same time. Then is there any other way with which we can realize a 3:8 decoder if both are enabled? Well, now that is a bit of a challenging task. The question here is both the decoders are enabled. So we cannot now use any variables to make them active or inactive. Now, how would we go about doing this? How would we go about doing this? It is possible, but you will have to apply some of your own logic. And that I leave to you as an exercise to find out. Without using any variable for the enable logic, by enabling both the decoders at the same time, how can you realize a 3:8 decoder with unique output? That is, any one out of these 8 will be 1 at any given point of time, not 2. So in this particular lecture, we saw how to work with decoders. We saw how to use the enable logic, how it is not very different from that of a mux. And thereafter, we saw how we can realize larger decoders using number of smaller decoders. Thank you.